All right, guys, there you go. Covalent bonding part 2. Here's what I need you to do. Here's what you need you to do. Draw the Lewis dot structure for ozone. Guys, for those of you that don't know, ozone is O3. You know that oxygen is diatomic. It is O2. Ozone is O3. So briefly, in your notes, draw the Lewis dot structure for ozone. All right, so we've got O3, O. I'll get you started. How'd I do? Somebody once tried to make this into a triangle.
I was actually doing that.
It's not a triangle. Molecules this small have a really hard time forming triangles. So guys, continuing on, we've got 18 valence electrons, 4 on the board. That leaves us 14. We have? Really? Did it what? We did carbon dioxide last time.
You showed us this at the very beginning of the unit.
Yeah. So, guys, let's play with this, shall we? So, we've got 14 valence electrons to get on the paper. You know that it doesn't matter where we put them. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So now we've got all the valence electrons on the board. And as we look at this, we realize that that central oxygen does not have a full octet. So what are we going to do? We're going to form a double bond. But guys, this is today. You ready? So let's make sure you're clear. We draw it like this. We understand the central oxygen doesn't have a full octet. We know that we need to create a double bond. The theme for today is the answer to this question. Where? Where do we draw the double bond? Do we draw it to the oxygen on the left, or do we draw it the oxygen to the right? The answer is it doesn't matter. So guys, we could go to the left, we could go to the right, doesn't matter. I'll go to the left just cause, and now we've got this, and everybody's happy, and that gives us the Lewis dot structure for ozone. Now guys, realize that if you had drawn the double bond to the right, that's fine, just flip it over, and then we got the same thing, right? Is that okay? Can you see that three-dimensionally? Maybe it would be helpful to build it. I think I've actually got oxygens that will allow this. Maybe I don't. Huh. Yeah, I thought I had oxygens that were drilled with 3 holes. Oh, there's one. So, guys, when we build this then, it goes like this, and it goes like this, and it goes like this. And so if you drew it like this, that's great. If you drew it on the left, it's still great. It's the same thing, right? It's just the other side of the same molecule. Is that okay? Okay. So now, guys, that we've got the Lewis dot structure for oxygen, allow me to share with you something that's really kind of interesting. So, guys, it goes like this. When we talk about the ozone molecule, it looks like this. But now we need to talk about something interesting about single bonds and double bonds. So we have drawn this with the single bond on the left and a double bond on the right. But there are some things that you need to know about single bonds and double bonds, but I think you can probably figure this out. Which is going to be stronger, a single bond or a double bond? Why are double bonds stronger? Additional electron sharing. It creates an additional region of increased electron density. There's more negative in here, so the nuclei are more attracted to that negative, and that makes that bond stronger. Does that make sense? Okay, so guys, if the double bond is stronger, what about its length? Will a double bond be longer or shorter than a single bond? Shorter. Stronger bonds are shorter bonds. Does that make sense? I like that some of you are writing that down. That's important. Stronger bonds are shorter bonds. Therefore, triple bonds are shorter than double bonds, and double bonds are shorter than single bonds, because triple are stronger than double than single. Does that all work in your brain? Okay. Now, guys, this is interesting. If you take an ozone molecule, and if you study the bond lengths of these molecules, do you guys know how they do this? It's really cool. It's called X-ray crystallography. Actually, what they do is they take these molecules and they freeze them. They lock them in place and then they hit them with X-rays. And the analogy is, have you ever taken like a garden hose and sprayed it through a screen door? And you know it splatters, right? Well, guys, if you can capture that splatter, you can actually work it backwards and figure out how big the holes are in the screen. You know what I'm saying? The splatter pattern tells you things about the thing that's creating the splatter, in this case, the screen. That's how X-ray crystallography works. If you take a substance and if you freeze it and then hit it with X-rays, you get a scatter pattern behind the stuff, and you can actually work it backwards and figure out how big the spaces are between the atoms, which gives you the bond length. Some pretty neat science. Well, guys, regardless, the idea is this. If you study an ozone molecule and measure the lengths of these bonds, that bond, it turns out, is 1.278 angstroms. Got it? So, guys, if that bond is 1.278 angstroms, what's this one going to be? Shorter, right? Well, guess what? It's exactly the same. That's it. So, guys, we need to talk about this. And this is the point of the day. It turns out that when you X-ray crystallography, when you measure the bond lengths in ozone, the bonds are exactly the same length. But here's the thing that's interesting and troubling. Guys, this bond length, 1.278 angstroms, actually sits between the length of an oxygen-oxygen single bond and the length of an oxygen-oxygen double bond. It turns out that it is shorter than a single bond, yet longer than a double bond. So the question then becomes, what on earth is going on? First of all, how can these bonds be the same length? But second of all, how is it that it sits right between the length of a single and the length of a double bond? What's going on?
Sort of like electrons where they aren't like set or neutrons.
It's not. No, this is not a probability thing. This is a thing. Go ahead. Yes, and if you ever write down 1.5 bonds, I will kick you in the shin. But guys, that is actually what is going on here. Remember when we started this, we were back here, and we were here, and we were here, and we got to the point where everything was single bonded together, and we had to ask ourselves the question, where do we draw the double bond? Do you remember that moment? And guys, we just chose arbitrarily to draw that double bond to the left, but we also said that we could have drawn it to the right, and we even went as far as to make the point that those two locations are equivalent. Get the idea? Guys, it turns out that that is not what happens in nature. Just allow me to redraw this, and we understand that we started here. And we said, what direction does the double bond go? And we said, could be left, could be right, pick one and do it. Guys, it turns out in nature, nature doesn't pick one and do it. What nature does is it creates a partial double bond in both directions. How does that explain what we experience in terms of the bond lengths in ozone? First of all, does it explain why they're the same length? Yeah, because they are the same bonds. And Matt, for now, we're going to call them 1.5 bonds. But guys, don't ever call them 1.5 bonds. But for now, we're going to say that. So guys, these 1.5 bonds are the same bond in both directions. But guys, remember the other thing that I told you. This 1.278 angstrom bond length that this bond is and that bond is shorter than a double bond, but longer than shorter than a single bond, but longer than a double bond. How does that jive with what we're experiencing? Go ahead.
Just like the same way the order 2 is between 1 and 3, it's just the average.
An average is actually not a bad way to think about it. But guys, let's see if we can talk about it more generically. So guys, which is shorter, a double bond or a single bond? A double bond, right? So a double bond is shorter and stronger. A single bond is larger, longer, and weaker. So where would we expect a 1.5 bond to fall? In between the two. It will be, again, shorter than the long, weak single bond, and yet longer than the short, strong double bond. And in fact, this is in between. It's actually not perfectly the average, but it is, in fact, in between. So guys, here's what we now know. When molecules form, and when they can form with double bonds forming in multiple equivalent directions. And guys, it's got to be equivalent. If this atom over here was a sulfur, this wouldn't work. They not only have to have the choice, they have to be equivalent. But guys, when we get in this instance where we could form double bonds in multiple equivalent directions, what happens is they form partially in both directions simultaneously. Now, Brandon, you asked the question sort of under your breath. You said, can they do this, right? It's like, really? Can they do this? Well, guys, what you're going to find out is, well, for now, yeah, they do this. But on Wednesday, we're going to talk about what allows this to happen. To understand how this happens, you've got to understand the process of hybridization. And I'm going to teach that to you on Wednesday. So for now, just take on faith that this works. And then when I see you on Wednesday, we'll talk about why, because we'll talk about hybridization. Go ahead. And that's the problem, right? How do we draw this? And the answer is no. So let me go to a clean slate. And let's talk about how we draw this. And this is basically, let me teach you everything we're going to do today. So, guys, do you see the problem here? Now, it's too messy. You don't see the problem. Let me show you the problem. So the problem that we run into is this. If we draw it like this, and then if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Those are all of our valence electrons, right? But now, if we draw in our half bond, which we're never going to call it, but if we draw in our half bond, now we've got too many electrons, right? Because we've got our 18 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, but then we've got this half bond. And we need to have a total of 18 electrons, but if we draw in the half bond, where do we take them from? Do we kind of like take half of one there and half? And the answer is no. So guys, the bottom line is this. This is not how we represent this phenomenon. So let me explain to you the way we're going to represent this. what we're going to do is this. Guys, I'm going to draw lines to represent electron pairs. You're welcome to do this. That's the two ways this can go. Bond on the left, bond on the right. Double bond on the left, double bond on the right. Which one does it actually do? Yes. And guys, understand, it is not flipping back and forth. It is doing both partially simultaneously. So guys, the way that we draw this is we draw both of these structures with a double-headed arrow in between them. Now guys, and this is going to seem wildly nitpicky, ready? You cannot use that arrow. What does the bottom arrow represent? Equilibrium. This is not an equilibrium. On the AP test, they actually make you know that. It is a double-headed arrow, but not an equilibrium arrow. No, they do. Right. Yes. Good. Yeah. Yes. Because equilibrium, as in equilibrium chemical reactions, implies a back and forth, when in fact it's a partial both simultaneously. Yeah, Jake, that's exactly why. Yep. Yeah. Did you understand what Jake said? That's worth mentioning. Guys, that if you represent it like this, that equilibrium arrow, from our understanding of equilibrium, is talking about a process that recycles. This is not recycling. They both exist simultaneously. And partially. Right. So, how do we talk about this? Guys, this is really important. You've got to learn the language of what we're talking about here. So after this, you may no longer call these 1.5 bonds. Do not call them 1.5 bonds. So what is the terminology that we use to describe this? And so guys, the terms go like this. So we understand that we're going to write ozone like this. So don't write any of this down, but this is the idea. This is everything you just learned. Print the notes if you need. So here's what we know. These two structures are equivalent except for the placing of the electrons. This is all review. So the Lewis dot structure for ozone, as Jake said, is actually the average of both of these. So what we do is we represent both of these conformations. And so guys, I'll give you this word again in a minute. Each one of these is what is called a conformation. And we separate them with a double-headed arrow. Guys, understand though that ozone does not oscillate between the two. It is truly the average of both structures, both conformations. You get the idea? Okay, so what are we going to do then for terminology? Write this down. Here are the words that you want to use. So first of all, how do we describe this phenomenon? And the answer is resonance stabilization. So guys, ozone is what is considered a resonance stabilized molecule. Now, when we talk about resonance stabilized molecules, this means that they have multiple structures. What do we call those structures? Conformations. But understand, I said that kind of wrong. Ozone doesn't really have multiple conformations. It's the average of these multiple conformations. But guys, there's another word that you'll hear used other than conformations. They are what are called resonance structures. So resonance structures and conformations can be used interchangeably. What?
So resonance structures and conformations
are the same thing. So let's do it in a sentence. Resonance stabilized molecules have multiple conformations. True.
conformations being
hold on. Resonance stabilized molecules have multiple resonance structures. Also true. So those two terms are used interchangeably. Okay, so what are the conformations or the resonance structures? That's these that we're separating with double-headed arrows. So this is a resonance structure or a conformation. This is a resonance structure or a conformation.
So, in other words, pardon my use of 1.5 bonds.
Let me give you a better term, and then let's talk. Guys, we are not going to call these 1.5 bonds. So what are they? They are what are called delocalized pi bonds. So what does delocalized mean? Without location. But isn't that descriptive of the fact that this double bond exists in both directions simultaneously? The pi bond part of it will not make sense until Wednesday. But guys, for now, if you can at least grab a hold of delocalized, you'll understand that that describes a double bond without location, which is what we're talking about. So now that, and again, don't ever call these 1.5 bonds. That is bad. Go ahead.
So the conformation is the entire atom.
So for ozone,
So when I say that ozone part 1,
this is one conformation, or wow, that's a long line. So this is one conformation of ozone.
so that's a, oh, let's see.
This that is the second conformation of ozone.
It's those bonds where that
No, this whole thing is a conformation or a resonance structure. This whole thing is a conformation or a resonance structure.
So our use of conformation or resonance, that does not exist in nature. It's our way of describing something.
Correct. Right. So do these conformations actually exist? No. The actual molecule is an average of all the conformations or resonance structures. So ozone never exists like this. Ozone never exists like this. It exists as an average of the two, where this double bond exists simultaneously, partially, in both directions at the same time.
That's the way that we actually show
But
that
that's the
average
way,
bond.
right, because if we didn't, we get back to Matt's problem. If we don't, then we can't represent the 8 valence electrons because we don't have a convention for showing partial bonds in multiple directions. So let's just work to the west, the east. Go ahead.
I noticed one of the oxygens has extra electrons, so does it behave the same way the bond does?
Where? They all should have 8.
They all have it.
No, when one of the oxygen has 2 extra electrons, when you combine them, does that extra electron spread out? Basically, what I'm asking, is that a polar molecule? Because it looks like it should be polar, but
Yeah, so your question is good. I want to talk polarity, but I'm concerned that you're saying that one of these oxygens, when you say extra, you don't mean more than 8, you just mean unbonded?
well, I just mean like one of the oxygens has 3 unbonded sites, the other one has 2 unbonded sites.
Yes.
So does that carry on with this phenomenon? Whatever.
No, they all have 4 bonds.
I mean,
You mean unbonded pairs. So this one's got 2 bonded, 2 unbonded. This is 1 bond, 3 unbonded. Yeah.
Does that carry on, or does that unbonded member spread out?
Oh, yeah, no. Okay, so again, don't ever draw it this way. But really what we've got, if you want to try to draw the overall structure, you would have a partial bond like this, a partial bond like this, and then this electron here, I forgot I could do that, would partially exist on this oxygen and partially exist on this oxygen. Yeah, so relative to that, it would be symmetrical, but it's still polar. The reason that it's polar is because it's actually bent. This is a trigonal planar molecule. Because there are 3 domains on the central oxygen, it actually is trigonal planar. It's bent. And so as a result, it's polar. Yeah, go ahead.
So you said you could replace it with one of these outside.
Correct.
If the middle one was a sulfur, would it work?
Yes.
So
Yes.
it has to be symmetrical.
So sulfur dioxide is also resonance stabilized.
Because H is water?
Because you can't double bond to hydrogen.
Oh, that's right, yeah.
Yeah. But yes, sulfur dioxide, SO2, don't confuse that. Never mind. SO2 is resonance stabilized. Yes. Go ahead, Becca.
So should we never draw the resonance stabilized molecule because then there's an electron
Well, let's say it this way. The way to draw resonance stabilized molecules is by representing all the conformations. That's how we do it. Okay, so we'll draw them like this. Go ahead.
What happens when you have like these huge, harmonic compounds?
Yeah, right. So let's take
The resonance structure.
well, yeah, and you can get a lot, right? But let's look at one that's maybe a little more interesting. Guys, draw nitrate. Put nitrate in your notes. Actually, you know what? Time out. Don't. Hold on. Let me just do this. We've talked about how we are going to talk about this. I'm scared that we're going to forget to finish this conversation. Here are the no-nos. 1.5 bond. That's a no-no. The other no-no is resonance bonding. There is no such thing as resonance bonds. These aren't resonance bonds, they're delocalized pi bonds. Be careful. Put those on your no-no list and then do nitrate. What do you want?
If we're doing structures, do we do them with the straight lines or do we show it the
I don't know what straight lines are.
dash lines? That's not right.
Yeah, no. Dash lines, bad.
Dash lines is bad.
Dash lines equal.
Electrons are individual.
So guys, allow me to catch up with you. We've got NO3 minus. I hope it's okay to say, obviously, the oxygen is in the middle. I'm going to draw this trigonal planar because I know it is. If you didn't know that, that's fine. Then, guys, we've got, well, you know what? Maybe I won't. All right, then we've got 5, 18, and 1 electron. So that's 24 minus 6 gives us 18. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18. What? Those aren't dashed lines.
When I said,
These
can
are-
you use, no. That's not what I meant when I said dash lines. When I said the electrons are separate, so we're showing this bond is.
You may draw what I drew.
Okay, thank you. So,
Okay, so guys, are you all with me to here? Okay, so then the question becomes, how do we give nitrogen a full octet? A double bond. Again, where? It doesn't matter because all three of these oxygens are equivalent. So guys, when we represent this then, we are going to do this. But then we also have to acknowledge then we also have to acknowledge that this works. And then we also have to acknowledge that that works. And then we need to represent that these are resonance structures or conformations. So we need to separate them with our double-headed arrows. But then, as Joel's pointing out, we need to also respect the fact that these are polyatomic ions, which means they are then properly cast in brackets with charges. This is how we represent nitrate. So nitrate is a resonance stabilized molecule. Nitrate has, and notice I'm using these words correctly. Guys, nitrate is a resonance stabilized molecule. Nitrate contains delocalized pi bonding, and nitrate exists as a resonance stabilized molecule with 3 different conformations or resonance structures. Do you buy all of that? Okay. Now, guys, let me sort of do a little foreshadowing with you relative to what this is going to look like when we talk about what delocalized pi bonding actually looks like on Wednesday. Guys, open your books to page 356. If you look in the left-hand column of page 356, the left-hand margin of 356, guys, the top diagram is what nitrate would look like if that double bond was not delocalized. You'll notice that they draw this with one double bond oriented to the right. And guys, that pink cloud that you see that wraps around top and bottom, that is the second bond in the double bond. We'll talk more about that on Wednesday. But what we're finding out is that this is not what nitrate does. How do we know? Because nitrate did this, what would be true of that bond on the right compared to the other 2 bonds? It'd be shorter. And it's not. The bond lengths in nitrate are all the same length. So what explains that is nitrate actually looks like the bottom molecule. This is really what nitrate does look like, representing that double bond existing partially and simultaneously in all 3 directions at once. Again, guys, for this to make sense, you've got to understand how this delocalized pi bonding works, and we'll talk more about that on Wednesday. Rachel, go ahead. Where is the double bond? I don't know. No, keep going. Are we okay? Okay. So guys, again, this is a little bit of foreshadowing relative to Wednesday, but I at least wanted to show you what this looks like when a multiple bond exists in multiple directions simultaneously. Go ahead.
So we need to represent all the structures?
Correct. Yeah, so guys, if you allow your eye then to drift a little bit further to the right, you'll notice that in that blue box, they have drawn exactly what we have on the board, right? They've got the 3 resonance structures, the 3 conformations. They've drawn them in boxes, in brackets with charges representing that they're polyatomics. They've separated them with the double-headed arrow that is not the equilibrium arrow. Guys, this is what that looks like, but that's the same as this. Yeah. What's the difference?
Oh,
What?
can we just do a single line?
Oh yeah, no. You call my arrows ugly? Come on. I'm big enough to take it.
So, like, even
No, that's fine.
even when there's like massive structure, like you're gonna like spiral out of area.
Well, yeah, check this out. Go back a page. Yeah, take a look at the bottom of 355. Yeah, that's a molecule called benzene. It's a C6H6. the things that you will be exposed to will be limited. They're not going to give you these crazy organic compounds where there's resonance structures going in 11 directions. Yeah, you'll see in homework. Yeah.
Now, is it essential for us to draw these as trigonal planars on the ADHM?
No. When you draw Lewis dot structures, let's back up a second. We understand that because this has 3 domains, it is trigonal planar. But you can draw them like this. You still need to understand that these are functionally 120-degree angles, but you can draw them like this. That's fine. They do not expect, like you could draw water like this. That's fine. You got to understand it's actually bent and therefore polar, but if your Lewis dot structure doesn't accurately represent that 3-dimensional reality, you're fine. Okay. You guys good on resonance? You're okay? All right, so guys, we're almost done. We're going to do 2 more things really quickly. And it goes like this. I am not going to give you time to write down notes. I know that drives you nuts, but I don't care. Guys, all of this is common sense. Well, all of this is common sense. All the rest of it is foreshadowing. You ready? So let's do common sense. That's going to kill you. No, let's don't. Okay, common sense. Remember when we started the day? And I said, which one of these bonds is stronger? And you said the double bond. And then you said, which one of these is shorter? And you said the double bond. Guys, that is all about bond strength, which we call bond enthalpy. So, how do we know which bonds are stronger than others? The answer is we break them. How do we break them? We add energy. How much energy is necessary to break a bond? That is what is called bond enthalpy. So guys, enthalpy, which you understand is heat or energy, bond enthalpy is the amount of energy needed to break a bond. Okay, now we measure that in kilojoules per mole. Does that make sense? How much energy does it take to break a mole of bonds? Okay, that works mentally. Then, guys, we learned something. Double bonds, well, let me ask it as a question. Double bond, will its bond enthalpy be higher or lower than a single bond? Higher. Triple bond, you're done. Guys, that's what all of this says. So, if you want this in writing, print the notes, but it just goes like this. So, guys, bond enthalpies are the amount of energy needed to break a mole of bonds. These are always positive values because energy is always needed to break bonds. Then, guys, greater bond enthalpy, stronger bonds, right? More stable. That makes sense. We've already talked about that. Don't worry about this relative to Hess's law. This is Hess's law. Remember when we did Hess's law and we talked about energies of formation? That the energy that's released when a molecule forms is the amount of energy that's released when the bonds form. This all goes back to Hess's law. But then, guys, we understand there's an inverse relationship between enthalpy and bond length. The stronger the bond, the shorter the bond, the weaker the bond, the longer the bond. You guys good? All right. Then, guys, this. This is where we're going to transition into Chapter 9. So, guys, when we get into Chapter 9, we are going to start to talk about molecules that violate the Octet Rule. We're going to talk about trigonal, bipyramidal, and octahedral structures. So please don't write any of this down. This is foreshadowing for Wednesday, but I wanted to at least I just realized, you know how I told you we were going to do hybridization on Wednesday? It's on Friday. I was wrong. Wednesday, I forgot we still haven't gone over the structures of the trigonal, bipyramidal, and octahedral. So we'll do that Wednesday. We'll explain it with hybridization Friday. So guys, here's what you need to know. We are now going to run into a lot of the weirdness with molecular structures. First of all, you're going to see some molecules that violate the Octet Rule because they have an odd number of electrons. An example of this would actually be boron trichloride. Guys, this molecule exists. boron trichloride exists. What's the problem with boron trichloride? Boron doesn't have a complete octet. Is it possible for boron to get a complete octet? Well, in theory, we could take some electrons off of here and do that, which then makes us realize it could be resonance stabilized. But guys, it doesn't. When we look at boron trichloride, we know that it exists, and we know that it is not resonance stabilized, and we know that there is not a single double bond with any particular chlorine. It happens. So guys, it is possible with these smaller elements that they can actually create molecules that don't complete full octets. What allows it? There isn't a lot of shielding. Boron's only inner core electrons are the electrons in the 1s. So that nucleus has got pretty direct access to even its second energy level electrons. And that's strong enough of an attraction, a Coulombic force, that it allows this molecule to exist stably because there isn't a whole lot of shielding. So it happens. All right. What's that? Yeah, but I guess what I should say is an odd number of electron pairs. Yeah, you know what? Let me actually do that. Odd number of electron, that's a better way to say it. Okay, so thought number one. So then moving along, guys, the other thing that we're going to find out is that sometimes we're going to find elements that have less than full octets. Again, boron trichloride is an example. But again, a lot of times these things, oh, wait a second, that's not what I was thinking of there. No, that should be electrons. You can actually, I wonder if, oh, look, it just let me do that. I'm sorry, I should have been looking ahead in my notes. Actually, boron trichloride is an example of this, one that has less than an octet. And so, guys, with this one, we understand that they don't tend to form double bonds because it's not favored, so they stay put. Molecules where there's an odd number of electrons, they just have an odd number of electrons. There's compounds like with things that, like aluminum that tend to do that. Then the thing we're really going to get into in the next unit, in the next days, is these molecules that have, are you leaving?
I have to go.
Okay, that have more than an octet. So guys, let's talk about this really briefly, and then we'll get into it a lot more on Wednesday. So guys, when we look at molecules where there's more than an octet on the central atom, this only begins to happen for atoms in the third period. So it only happens, well, it only starts to happen right here. So guys, the first elements that start to do this are these, like phosphorus, sulfur, and chlorine. These elements up here cannot have more than a full octet. The reason is where those extra electrons go. Because you know valence electrons are only the s and p, right? So the valence electrons, 2 in the s, 6 in the p, you're done. So what happens when these atoms get 5 and 6 pairs of electrons? And the answer is those extra electrons go into the d sublevel. The d sublevel becomes valence. But guys, the third energy level does not have it, I'm sorry, the second energy level doesn't have a d sublevel. So these dudes cannot have more than an octet. These guys can, but now you're thinking, wait a minute, if these are in the 3p, we haven't got to the 3d yet, so how can they have more than an octet? And guys, the answer is the third energy level has the potential for a d, even if it hasn't been started yet. So these are the elements that begin the possibility of having more than 4 pairs of valence electrons because they have the potential for a d.
I just read your clock.
Oh.
10.
Oh, there you go. Oh, yeah, we didn't set that back yet. So guys, they have the potential to have a d even though it hasn't happened yet. Okay, so things that you need to keep in mind. So this is where the d sublevel comes into play. So guys, these elements in the 3p behave as if they have a D, even though it technically hasn't started to fill yet. So you can get things like PCl5, where phosphorus can actually bond to 5 chlorines. Now the other reason that this happens is also size. These smaller central atoms don't have enough surface area to pack more than 4 elements around. But guys, when we get a bigger atom like phosphorus, that atom is physically bigger and we can get more other atoms packed around it. So guys, this is what we're going to talk about next time. We're going to talk about all of the geometric structures. We're going to talk about elements that don't have a full octet. We're going to talk about elements that have more than a full octet, and then we're going to explain it on Friday. You got the idea? Okay. So guys, here then is your homework. It's short.
Lovely.
In addition to this, please remember that we are going to summarize Chapter 9. And we are done at 11:25, gives us 7 or 8 minutes. And guys, we'll dig into Chapter 9 next time.